So for our next topic, we'll be looking at Fanning's friction factor. And in this question, we want to be proving that the Fanning's friction factor for laminar flow is equal to 16 divided by the Reynolds number. So in order to do that, we'll do a pressure drop experiment. So we have a horizontal pipe here with some radius, large R, and it has a flow rate going through it of Q. And in this, we have a column of fluid with radius small r. We'll be doing a force balance on this fluid on this column of fluid as our first step. So the two forces that are acting on this column are the pressure forces at 2 and 1, and then there will be a shear stress on this as well. So the pressure forces, because it's a pressure drop, P1 will be larger than P2. We'll be multiplying that times the cross-sectional area on which it acts. And both of these forces act on the cross-sectional area of this column of fluid, which is pi r squared. And then the other force is shear stress and the area that it acts upon, which will be the entire outer circumference of this column. So it will be 2 pi r times the length of the column that we'll call delta x. So now that we have this, and we know that it's equal to 0, we can sub in for shear stress we'll sub in mu dV over dr. And that's true for all Newtonian fluids. The shear stress is equal to the viscosity as dV dr. Then we have 2 pi r delta x equals 0. So we can cancel a few things, a pi will cancel, and an r will cancel. And now we want to separate the dV dr. So doing that, we get dV dr is equal to negative P1 minus P2 r over 2 mu delta x. So now that we have this separated, you can see that we can integrate. So we move dr over, and then integrate. This gives us V is equal to negative P1 minus P2 all over 4 mu delta x r squared. And because there's no limits of integration, we have to have a plus c for a constant. What we want to do first is figure out what this c is. So in order to do that, we need to plug in a V and an R that we know. So we know, because it's laminar flow, the velocity profile will look something like this. And as you can see from this, the velocity at the outer radius of the pipe will be equal to 0. So we plug in V is equal to 0, and R is equal to uppercase R, gives us 0 equal to negative P1 minus P2 all over 4 mu delta x r squared plus c. So now you can see that c is equal to P1 minus P2 over 4 mu delta x r squared. So now we plug this back in here, and we can get our function for the velocity of the fluid. P is equal to P1 minus P2 all over 4 mu delta x times large R squared minus small r squared. So you can see I plugged it back in, and then I factored out the P1 minus P2 and 4 mu delta x. So this will be our function for the velocity of the fluid at any given radius. So now that we've derived the equation for the velocity of the fluid, we want to relate that back to the volumetric flow rate of the fluid. So to do that, we use the simple equation Q is equal to the integral of V dA. And to figure out what dA is, we're going to turn this, so we're looking down the end of the pipe. So if this is our differential area here, you can see it's a circle. So it's going to be the circumference of the circle 2 pi at some radius r times the differential radius there. So dr. So now all we have to do is plug in our velocity profile that we found earlier. So Q is equal to P1 minus P2 all over 4 mu delta x, r squared minus r squared times v 2 pi r dr. So we can factor a few of the constants out, and that'll give us Q is equal to P1 minus P2 times, accidentally brought that E down, times 2 pi all over 4 mu delta x times the integral of r squared times r minus little r cubed, and that's all multiplied by dr. And so now, because we want to capture the flow rate of the entire vessel, we're going to integrate from 0 to large r, because that's the outermost radius. So now we can evaluate that. We get Q is equal to P1 minus P2 times pi. These 2's will cancel. It'll leave me a 2 mu delta x on the bottom. And then we get r squared over 2 minus r to the 4th over 4, evaluated from 0 to r. That gives us P1 minus P2 is pi over 2 mu delta x. And this leaves us with r to the 4th over 2 minus r to the 4th over 4. So here you see we have basically 1/2 minus 1/4. So that's going to leave us with 1/4. P1 minus P2 times pi over 2 mu delta x times r to the 4th over 4. So again, we can combine these two numbers, and that'll give us an 8 on the bottom. And this will be our formula for the volumetric flow rate of the fluid. And as you can see, everything in here is a constant. So this will be a constant Q based on the pressure drop. So now that we have this function of volumetric flow rate, we want to solve for the pressure drop in order to plug it into Bernoulli's equation. So the pressure drop, P1 minus P2, is equal to 8 mu delta x times Q over r to the 4th times pi. And because the frictional heating has diameter instead of radius, we're going to go ahead and change this radius to diameter. So the radius equals 1/2 diameter, so that gives us P1 minus P2 is equal to 1/28 mu delta x Q all over r to the, or d to the 4th rather. D to the 4th times pi. I also want to go ahead and change this Q into the velocity times the area. So I'll have P1 minus P2 is equal to 1/28 mu delta x v, and then the area will be pi d squared over 4. Pi d squared over 4, and that'll be d to the 4th with a pi. So now you see we have some stuff to cancel. Pi cancels, the d squared cancels, 4 cancels, leaves us with 32. And so this leaves us with P1 minus P2 is equal to 32 mu delta x times v all over d squared. So now we need to use Bernoulli's equation. So Bernoulli's equation, we have P2 minus P1 over rho, change in pressure head. And then because there's no change in geometry of this, A1 is equal to A2, there's going to be no change in the kinetic energy head, and it's also a horizontal pipe, so there's going to be no change in the elevation head. So that means all we have for Bernoulli's equation is P2 minus P1 is equal to negative frictional heating. However, we want this to be P1 minus P2, because that's what we solved for here. So we're going to flip that around, and that'll also be handy in getting rid of the negative in front of the frictional heating. So now we just need to substitute this in, and substitute in what our frictional heating is in terms of the fanning friction factor. So that leaves us with 32 mu delta x v over d squared times rho is going to be equal to 4 f delta x over d squared over 2. So delta x on either side can cancel, d on either side can cancel. This 4 and this 2 cancel, leaves us a 2 here. Then divide that across gives us 16. So now we're left with 16 mu v over rho d squared is equal to the fanning friction factor. And we still have a v that we need to cancel. So 16 mu over rho dv is equal to the fanning friction factor. And if this mu over rho dv looks familiar, it's because we know the Reynolds number is equal to rho dv over mu. So flipping this around, we can see that 1 over Re is equal to mu over rho dv, which is exactly what we have here. So plugging that in gives us fanning friction factor is equal to 16 over Re. And there's the proof of it. So that's how we derive the equation to prove that the fanning friction factor for laminar flow is going to be equal to 16 over Re. Thank you for watching today's videos. I hope you enjoyed them. I hope you learned a little something. Today we discussed Fanning's friction factor, we discussed the properties of a flow meter, and we also discussed sudden expansions. So I hope to see you next time when we dive more into chemical engineering.